Hi. Hi. So, okay, so I'm Nasser, also from Professor Zahid Hassan's group at Princeton, and I'll be talking about the ARPES measurements and the experimental observation and discovery of the Weyl semimetal materials, being the tantalum arsenide class of materials. And so my colleague Suyang earlier in this session gave a very nice and complete survey of various theoretical and experimental aspects of Weyl semimetals. What I do here is to pick up from very left and focus on the experimental data. So here is our group at Princeton University in Professor Zahid Hassan's group, and here are the members of the group and a list of our collaborators who grow very nice samples for us and conduct first principle calculations and theoretical analysis for us, as well as our collaborators, our beamline scientists at various national lab synchrotron facilities that help us with our ARPES measurements. Okay, so as I said, I'll focus on our work regarding the discovery of Weyl fermion semimetals and topological Fermi arcs in tantalum arsenide that was done last year and published last year, and I will talk about some of the follow-up works as well regarding the spin resolved ARPES measurements and some of the related materials to tantalum arsenide. But for a lot of other work that were done at our group during the last year on these materials, here's a list of publications that you can refer to, both on the theoretical side, ARPES side, STM side, and first principles calculations and transport side. Okay, so now people in this session have already talked about tantalum arsenide, but I'll just refresh your minds. So tantalum arsenide crystallizes, it's a semi-metallic material that crystallizes in the body-centered tetragonal lattice with layers of tantalum and arsenide interpenetrating each other, and they are shifted relative to each other. And it results to a Brillouin zone that's shown in the left corner picture. So now, in the absence of spin-orbit coupling, our first principles calculations on the top row, they show that the bulk valence band and the conduction band interpenetrate each other, and they form four 1D line nodes that are closed loops. But when we include the spin-orbit coupling, these line nodes, the spectrum will be gapped at certain momenta, and these Weyl nodes will be gapped, and they will shrink into, each of them will shrink into 6 Weyl nodes. Okay, so this is how they look. On the left, you can see the bulk spectrum without the inclusion of spin-orbit coupling. There are 4 line nodes on the xy equal to 0, kx equal to 0, and ky equal to 0 planes. And once you include the spin-orbit coupling, these line nodes will be gapped, and they will result into, each of them will result into 6 Weyl nodes away from the kx equal to 0 and ky equal to 0 planes. Okay, now, that means there are 4 Weyl nodes, each of them, there are 4 line nodes, each of them 6 Weyl nodes. That means there are 24 total Weyl nodes in the bulk Brillouin zone. Now, if we project these onto the 001 Fermi surface, so the ones that are denoted by W1, right? They would project onto the edges of the below zone, right, each of them to one point, right, and there would result to Weyl nodes with chiral charges of plus or minus 1, right? But the remaining ones, the remaining W2 Weyl nodes, they project pairwise onto the same point on the surface, Fermi surface, and because each of those have the same chiral charge, each pair has the same chiral charge, that will result to points along the gamma x or gamma y direction that each have plus or minus 2 chiral charge. Okay? So now, what does that mean? What does it mean that some of these have plus or minus 2 chiral charge and some of them have plus or minus 1? So very simply, it basically means that if you have a Weyl node that has number one chiral charge, there will be only one Fermi arc surface state falling into that or terminating on that Weyl node. Okay, so if you have two Weyl nodes that are plus 1 and minus 1, there will be one Fermi arc surface state that connects across these two. Okay, so now what we want to do is to show you our experimental data, and here is a Fermi surface from tantalum arsenide that we have measured by low photoemission ARPES that is surface sensitive, right? And you can see here that there are three dominant features, okay, in this Fermi surface on the left. The first one that has the rectangle around it is a crescent-shaped feature, right, between gamma x or gamma y. The second one is a bow tie feature around the x point of the below zone, and there is another extended feature around the y point. So now, if we focus on the crescent-shaped feature, we can see that it really looks like two open features that start from the same momenta on the Fermi surface in the below zone, on the Fermi surface, and they end at a different momenta, but the same. They end up on the same momenta. So all these are very consistent with our first principles calculations, as you can see on the right. Okay, but now how can we tell that actually the crescent-shaped feature is not a closed Fermi surface? Okay, so basically, how can we experimentally prove that we are seeing open Fermi surfaces that are Fermi arcs? So, to portray that, I will contrast what we are experimentally observing in tantalum arsenide with what we have observed in bismuth selenide, which is a topological insulator, or sodium tribismuth, which is a topological Dirac semimetal. So in bismuth selenide, the Fermi surface across a kx, ky Fermi surface across the topological surface states would result into a closed loop, right? A closed Fermi surface. And in sodium tribismuth, the two Dirac nodes would be connected as Suyang experimentally showed, that those two are connected by Fermi arcs. Okay, and those Fermi arcs are positioned on the two different sides of the Dirac nodes. So if you draw a line between the two, they would be positioned on the opposite sides. But in tantalum arsenide, what we see is that they are actually positioned on the same side, okay, of the line that connects the two Weyl nodes. But So what does that mean? How can we use that to show experimentally from our experimental data that these are fermions? So if you draw a loop around one of these Weyl nodes, okay, that only encircles one Weyl node on the surface Fermi surface, then as you go around this loop, right, you would see two co-propagating bands crossing the Fermi surface. Okay? And that's a sign that you have a chiral charge of 2, right? And so basically, now I'm going to elaborate on why this co-propagating feature is crucial in identifying these as Fermi arcs rather than any closed Fermi surface, right? Okay, to do that, let's first consider the Fermi surface that's resulted from trivial surface states or from the surface states of a topological insulator. And on the left, you'll see that if we change the energy, right, the two opposite points, and pick two opposite points on this Fermi surface, as we change the energy, these 2 points would travel in the opposite directions. Okay, so they are counter-propagating as we change energy. But what one would expect in the Fermi arcs is that if you pick two, like for example in what we have seen in tantalum arsenide, it would mean that if you pick the two opposite points on the momentum space, on the Fermi surface of the momentum space, as you change the energy, they would travel in the same direction. So basically they are co-propagating contours basically. And that would result to two branches or whatever number of Fermi arcs that you have that have the same Fermi velocity. And remember that that's not the case if you have like the top row, if you have a trivial surface state or topological surface states of a topological insulator. That would not be the case. The two branches, for example, would have opposite Fermi velocities. Now, to show that from our experimental data, what we can do is, as I explained before, take a loop, right, that encircles only one of these Weyl nodes, and go around it. And as you can see on the bottom plot on the right, we observe two surface states that cut across the Fermi level, and indeed they have the same Fermi velocity. Now, we can do something more as well, and take the Fermi surface, right, kx, ky on the Fermi, at the Fermi level, and a kx, ky map at a higher binding energy below the Fermi level, right, and subtract these two from each other. If you look at the top plot on the right, you can see that the red ones, right, after subtraction, the red ones move outward, right, and become the blue ones. So that shows that these features, these crescent-shaped features, are actually co-propagating, and it proves experimentally that what we have observed here are Fermi arcs, open contour Fermi arcs rather than closed loop Fermi surfaces. So what would be the next step? The next step would be to actually prove that we have observed linearly dispersive Weyl cones and Weyl bands. To do that, we conducted a high photon energy soft X-ray ARPES that favors the bulk bands, and if we set the Kz value of our if we set the Kz value by setting the photon energy to the position of the W2 Weyl nodes and map the Fermi surface, we can see that there are two dots in the box that we have indicated on the top left plot, and those two dots are the Weyl nodes. And how do we know that? If we take a cut of momentum energy, Ke, as you can see in the middle plot on the top, there are two linearly dispersive bands that cut across the Fermi level, and these are bulk bands. We have done Kz dispersion, and we can confirm that these are bulk bands. And so those are our Weyl cones. So we can see that we can show those linearly dispersive Weyl cones as well. Now we can also change the Kz value and set it on the W1 Weyl node and observe the Weyl cones of the W1 Weyl node. And we can also show that in agreement with theory, the W1 and W2 Weyl nodes are offset from each other in energy. Now, to summarize this part, what we do is to superimpose this soft X-ray ARPES data obtained at high photon energies with low photon energies, surface-sensitive measurements, to scale on top of each other. Okay? And what you can see is that there is a very good agreement between where the Weyl nodes are after superimposing them, and where the Weyl nodes are in the Boulogne zone, and where the two crescent-shaped features terminate. Right? You can see that the two terminate on the position of the Weyl nodes, which establishes very firmly the signature that and the proof that we have observed we have observed the Weyl nodes and the Weyl cones and the Fermi arcs that connect across these Weyl nodes. And again, we can just look at this. We don't necessarily have to compare this with theory. This is a very firm experimental proof of this. So we established this. We have a Weyl semimetal phase in tantalum arsenide. In the next step, what we do is we measure the spin polarization of these Fermi arcs. So let's start by the outer Fermi arc. First of all, our calculations show that these Fermi arcs, both of them, the outer one and the inner one, if you go around a loop counterclockwise on either of them, the spin polarization is in plane and it changes and it rotates clockwise as you go counterclockwise around the arc. So if we pick 5 points on the outer Fermi arc and do the spin polarization, we can prove that this behavior is actually right and the spin polarization is consistent with the theoretical calculations. Same thing for the inner arc. We can show that the spin polarization goes clockwise as we move counterclockwise along the arc. And this is all in plane. There is no out of plane spin polarization. Now, the last part that I'll talk about, and then I'll ask Suyang to continue, is that now we turn our attention to the other compounds in this family. The first compound, the second compound that we have measured is niobium arsenide, and we have shown that it's very consistent. The band structure, Fermi arcs, Weyl nodes, Weyl cones are very consistent, and similar to tantalum arsenide, with the difference, as the previous speaker also mentioned, with the difference that the arcs are much closer to each other. But if we measure TAP, tantalum phosphide, we see that, I don't know if that's clear or not, it's quite dark in here, I don't know why, but we can see that there are more features. Yeah, can you turn the light a little dimmer? Yeah, okay, that's better. So we can see that there are more features around the Weyl nodes in tantalum phosphide, right? That would be very counterintuitive. And one would say, how come if these two have chiral charges of plus or minus 2, how come you have more surface states merging into the Weyl nodes? But again, we go to the same method. We go back to the same method as I explained earlier. We take a loop around one of these Weyl nodes, okay, and go around, and we count the Fermi, level crossings, right? Here, we actually see 4 right-moving and 2 left-moving crossings, right? And that shows that at least 2 of these pairs, so 4 of these bands, have to form a closed loop, right? Because if there are Fermi arcs, they have to have, so by subtracting them we can conclude that, because if there are Fermi arcs, they have to be co-propagating. So at least 4 of these form closed loop Fermi surfaces, and that shows that they are trivial surface states. And as I have shown in the bottom plot here, this means that 2 of them terminate on the bulk Weyl node, but the rest of the bands are trivial surface states that come very close, but they do not merge into the bulk Weyl node. And here is our explanation that only 2 of those surface states are Fermi arcs, and the rest are trivial surface states that exist. So now I hand it to explain.
So can people in the back turn the lights on? And any questions?
Oh, yeah.
If not, let's go to the next talk by Florian Xu about
All right, so I guess my colleague and also the previous speaker has told you a lot about what ARPES can do, and that's very good. We know that ARPES is very powerful in topological business. But I'm going to tell you something about what the limitations, especially in terms of showing Fermi arcs. So before I go to that, let me just show you 3 calculations of the tantalum arsenide surface states. These are exactly the same. I only vary the surface on-site potential values. And forgive me that the color code is not consistent, but then you see that by changing the surface on-site potential, the detail of the Fermi arc, their dispersion and their connectivity changes dramatically. So that tells us that, in theory, if you just compare, let's say I have an ARPES data and it looks very similar to theory, it doesn't mean much because the theory can change so much by changing a free parameter, right? And also, that also means that, it's sort of meaningless to compare ARPES data across different groups, because when you cleave one sample, you have one particular, surface detail like potential and whatever on your surface in experiments, and then when you cleave the second sample, that detail can change. You don't know, maybe the vacuum is changing, or maybe many things can change. So keeping that in mind, then the question that we want to answer is, for a particular given ARPES data set, if we have that data, are there any scenarios that we cannot show that there are Fermi arcs? And indeed, those scenarios exist. So there are 2, basically I want to show 2 different things. One is that if you can't resolve the band very clearly, you cannot resolve the band very clearly, then you can't show whether these are Fermi arcs or not. This is quite intuitive. The second one is that even if you can show that what are the bands at the K-space area that you're interested in, still there are scenarios where you cannot show that these are Fermi arcs. So let me go to the first case. So as Nasser explained, that we chose this circular loop, and this is great because there are only these 2 crescent or moon-like shape bands there, and it's very clean. So then when you take a loop and ravel the band structure, you see only 2 band crossings, right? The black circle only cross the bands, the 2 bands. But people might ask, there are 24 Weyl nodes, specifically near the zone boundary. There's a different independent set of Weyl nodes. How about there? Can you show the Fermi arcs there? And our honest answer is no. And the reason is that the Weyl points there near the zone boundary, like highlighted by the white box, is extremely close to each other in momentum space. And at this particular choice of surface onset potential, the Fermi arc is just a straight line, extremely short. Obviously, that connectivity can change if you just change the surface potential or whatever, but it can change. But this is one example. So then, now, what if that you try to choose a loop that encloses one of these points? For example, look at this green big triangle. This is used by several groups, not us, but several ARPES groups. So now, your triangle will enclose both the, this +2 and this +1. Fine. Then you get you enclose net chiral charge of +3. That means around this loop you get an odd number of band crossing of your surface state. And let's count. So the crescent, the two muon, will give me 2 band crossings, and this big bow tie will give me 2, right? One here. So that's 4. So the last one would be this very short arc. So obviously that's consistent. But this is just perfectly in theory, and I blow this up. I'm assuming that this arc is very, very long. But then if the arc is in reality very short, then you can very easily have, in experiment, you can never say that you cut perfectly horizontally. What if you cut a little bit, away, then you miss that very short arc? So the claim that you see odd number of counting along this big triangle effectively means that you resolve this very short arc. And as you can see from the ARPES data, we just see the bow tie. We don't see anything in the middle. It's just a blur. So what we think, honestly, is that we can show that these two are Fermi arcs, but we don't know what's going on. According to theory, there are 2 Fermi arcs, there are 2 Weyl points and whatever, but we can't show that in experiment. So that's number one thing. So what I'm trying to say is, if you can't resolve the bands in this region clearly, then don't choose a loop that will enclose this area, because then you're sort of suiciding. So that's number one scenario. Number 2 is that what if we do see the bands clearly? So let's first just consider this cartoon. So I have this +2 -2 Weyl nodes. Then I'm going to say, okay, I have these 2 Fermi arcs. So now let me add a closed contour, which is this big lollipop. So the idea is that now you see that if I draw this loop, then as Nasser explained, you would get 2 band crossings which are co-propagating that arise from these 2 Fermi arcs. And now you can add arbitrary numbers of trivial contours. For example, here I'm adding 1. But no matter how many you add, you will always get an even number, because each closed contour will contribute 2 crossings. And if you add more, then you get an even number. So what I'm saying is, if you choose a loop, you get the absolute value of the chiral charge that is enclosed plus an even number that is trivial. So that's fine. But then if you look at our data, I was using the contour here. But many people have asked me, what about this direction? You see very clearly that except these 2 muons, there are these 2 parallel lines. Now this is bad, because now if I draw a closed contour here, you get 3 band crossings, but then your chiral charge is 2. And you can also see this in other people's published papers. So here again, you have a chiral charge of 2, and they have identified 5 things, A1 through A5. So now if you go through this loop, you get 5, but then your chiral charge is 2. Again, it's contradictory from each other. So this is the solution, but this also tells us the limitation of ARPES. So in order to see why that is happening, you have to consider the full band structure. So in the bulk, the bulk will project onto the surface. So except these 2 Weyl points, you actually have another trivial bulk band, because we know that tantalum arsenide is a very good semimetal, but still it's not perfect. There's still trivial bulk pockets. So exactly what happened is, except these 2 Weyl points, there's this trivial bulk pocket projection that comes very close to the Weyl point. So now I have these 2 Fermi arcs, and now I can add a trivial closed contour, but somehow that this is actually a contour, but then they are truncated by this bulk projection. So now this looks like a Fermi arc, but it's basically a closed contour that this area of the spectral weight is shadowed by the bulk band. So now I can draw a loop like this. So what happened is, unlike the previous case, my loop will go through this area that has a Bach band crossing. So what I mean is that at the Fermi level, it's not fully gapped. I have a small case section that is crossing this blue band. So now, again, these two Fermi arcs will give me this two chiral surface state. But you would have another one, which is this blue band, this blue trivial Fermi arc coming up. But what happened is that because it's trivial, it actually bent back. It doesn't connect the band gap. But now, because ARPES only observed the electronic structure below the Fermi level, so imagine that now I don't see the top part. Then effectively I see two bands going in this direction and one band going to the other direction, but I don't know whether it's bending back or whether it's going toward the conduction band. So then in this case, you're screwed. So basically what I'm saying is that ARPES is a very powerful technique in demonstrating the Fermi arcs, but if we are honest and if we're careful, then there are also scenarios that we can't show it strictly, but obviously you can always say, oh, we have this ARPES spectrum is so nice and so consistent with the theoretical calculation. That's something and that's good, but it's not a strict proof in the topological sense. That's all. Yes, please.
Can you go back to your front surface? So at X point, it looks like you have a double height.
Yeah.
Why is that?
Well, because this is strong spin-orbit coupled, so each band will have both spin ups and spin down. It's like a rush bar. But it doesn't matter. You have a double, then you get 4 number of crossings. Right? It's not always. Y point we can't resolve anything. We just see like this ellipse. It's just, yeah, I don't know.
Any other question? Yeah.
What do you mean by the surface potential?
Oh, thank you. So, yeah. So basically, you have this layer structure, right? So, it's not layered, but then it's, tantalum, arsenide, repeating. So now, you need to consider the following orbital to calculate the band structure. So basically, tantalum D, tantalum S, arsenide P, and arsenide S. These are the main orbitals that play a role. So now, in the bulk, the potential, this is a parameter in the DFT calculation. In the bulk, it's fixed. But on the surface, because you are next to vacuum, your potential of the atoms, like how you hop onto the atom, can be different from the bulk because you're not periodic, right? You break inversion near the surface. So now each layer you would have this orbital, and each orbital would have an onset potential, and these are sort of free parameters. For example, if you imagine you put some potassium atom on your surface, then that will, the potassium will lose one electron, then they're like potassium ion on the surface, right? That will have a very strong electrical field, and that will change the potential near the surface. It's like applying an electrical field that can change the scenario near the surface. Yeah.
Is it a primary in your tight binding calculation, or?
It's not tight binding. It's a DFT calculation.
And actually, are you considering the case where you dope with some?
Well, but the idea is that in DFT you don't know what is the scenario in the experiment, right? These are free parameters.
Right, but.
So effectively, if you want to change from these three scenarios, let's say you have a cleaved surface, you see a band structure that is similar to number 3. But you could, in principle, go to number 2, probably by doping potassium or, oxygen or whatever. And that will change the connectivity and the shape of the Fermi surface. That's seen in many things.
Right. So you technically you add some potential of some arbitrary profile.
Well, so this is our first, when we predict the material, we don't know. We just set arbitrary potential. We don't know what it is. But then this is the one that we use to match up with the experiment. When you have experiment, you can train your free parameter that makes your calculation look similar to your experiment. Many people do that. Yeah.
Okay, so maybe you can talk more.
Yeah.